Hi, this is Kunhan. I'm here to present our work HNDF, Hybrid Neural Diffeomorphic Flow for Shape Representation and Generation via Triplane. In this work, we explore the task of 3D shape representation and generation. Different from existing methods where the shape are directly represented as point cloud or mesh, the shape in our work is represented as the deformed template. The template is learned from training, and the deformation is encoded using hybrid field. The figure below shows the visualization of our results. On the left side, t equal to 0 shape is the learned template, and the t equal to 1 shape is the deformed shape, with the t between 0 and 1 as the intermediate shapes. We can see clearly the deformation process from t equal to 0 to t equal to 1. And thanks for the bidirectional deformation, the represented shape now share the same topology and color as the template shape. On the right side, we show the generation process for t equal to 2000 to t equal to 0, using the diffusion denoising process. The detail of shape representation and generation will be presented later. To have a global view of our project, the entire framework consists of two components. 3D shape representation is to learn the template shape and optimize the deformation for each individual shapes. 3D shape generation is to generate a new deformation and apply it to the learned template shape to get a synthetic 3D shape. For the 3D shape representation, because we want to have more accuracy in representing the 3D shapes, we try to combine the implicit representation neural field and the explicit representation triplane as the hybrid representation to represent accurate and complex deformation. Specifically, each shape I has its own triplane features to embed the bidirectional deformation to template shape using Neural ODE. For each position Pij, the deformation feature for this position is interpolated from the triplane feature as the input to the deformation module D. The deformed position Pij is then input to the template module T to get the predicted sign distance value Fij prime. We want to minimize the following difference between the real Fij and Fij prime to learn a general template shape for this class, and also the deformation module to represent the deformation for each shapes given the triplane features. Even though triplane feature provide high capability to model complex deformation, the high freedom of sampling during the training might cause optimization of triplane feature trapped in the local minimum and have bad representation results. Therefore, we propose the hybrid supervision to augment the previous random sampling with applied grid sampling. During the training, k by k coordinate grids are sampled, and then the training are combined with two new regularization, specially applied for this coordinate grid: the negative Jacobian determinant regularization and the deformation smoothness regularization. With this new regularization, we could ensure the diffeomorphism of the deformation field and maintain the structural integrity. In this way, we can have a global and local constraints for this shape deformation. After the training of previous 3D shape representation, we fix the deformation module and template module and optimize the triplane feature for each 3D shape in the dataset. The optimized triplane feature can be viewed as three 2D feature planes, which are aligned with the requirement of available diffusion model. We train a 2D DDPM to generate the triplane features. Then, the new shape is generated by deforming the learned template shape using the deformation encoded by the generated triplane feature. We compare the representation results with the state-of-the-art method, including NFD, NDF, and DIF-SDF. As shown in the figure, our method is able to represent the shape with high fidelity and low errors. Besides the shape representation, our method is also able to do the shape restitution between individual shapes. Thanks for the bidirectional deformation, represented by our deformation module. We also provide more visualization results to show the deformation process and shape correspondence. We then compare the shape generation results. From the figure, we can see the deep SDF and NDF achieve over smooth result, while NFD would bring more error as it directly represents the shape. Our method, however, is able to generate realistic shapes because of the high representation power of hybrid field and also the underlying template shape. We also provide more visualization results to show the generation process and the shape correspondence. Thank you.